Hello everybody, welcome to today's lecture. So today we're going to talk about 2.3. Last time we talked about 2.2, which was about location of center or measures of center, better known as the types of averages. So the mean, the median, and the mode. So let's just do a brief recap here. So we talked about the difference between mean, median, and mode. The mean is what we typically call the average. It's where you add all of the values up and then divide by however many there are. The median is our exact center. So if you put the data in order, it's the one in the exact middle. And finally, the mode is the one that occurs the most frequently, which is typically more reliable for qualitative data versus quantitative data. Qualitative being data that describes like qualities, like as you can see, we talked about like colors, days, religions, stuff like that. Quantitative data is the data that's usually represented with numbers. So mode is a lot less useful for that, like we saw in the test scores example, because a lot of times data values don't even repeat. Okay. And then we talked about how the mean is very influenced by outliers. So if there's a lot of outliers and we're concerned about it, then we typically would want to use the median. The median would be a better representation of what the average everyday person looks like. So, when you're deciding between the mean and the median, I mean, there's always no harm in finding both, first of all, and presenting both. But the one you want to focus on, it depends on whether you want like a weighted average or like a weighted center or like a or an exact center. Okay, and they both have their uses. And then we had some notation. So just remember this X bar and the sigma notation. X bar is for the sample mean. Sigma just means add everything together. So when you say sigma X, this means add, X represents our data. So this means add all of our data together. So like for the test scores, like this sigma X is just saying to add all of the test scores together, and then divided by n being however many there are. Okay, we use little n for the sample size, big N for the population size. And then we use the Greek letter mu for the population mean. Okay. Now the population mean and the sample mean are calculated exactly the same. You just add up all of the data values and then divide by either the number in the sample or the number in the population. In the next section, in 2.3, the one we're doing today, we are going to have to distinguish between the sample, what we're going to call standard deviation, and the population standard deviation, because we're actually going to calculate them differently. So it'll be important which one they're coming from. But typically when we're doing examples, we're going to be calculating the sample standard deviation. Because in practice, you're not typically looking at the entire population, you're just looking at a sample, right? So this section is called measures of spread. Okay, measures of spread. So what we mean by this is we want to measure how spread out the data is. Okay. Usually this means like how far away is it from the center. Okay. So in our test scores data that we had way up here now, or right here, you can see like these two data values, the first two are 40 apart from each other, whereas some of the later ones, like the last two, are only 7 apart from each other. So how far apart they're spread out, it's very different. What we want to do is we kind of want to look at, okay, on average, how much is their data spread out? Okay. So, these values, meaning the measures of spread, or variability, sometimes it's called variability. So how much does our data vary? Measures of spread or variability. These values describe how spread out a data set is. Okay. These values describe how spread out a data set is. So there's a few different types of these that we can look at. The first one is a range. This is probably the simplest way. Okay, the range. The definition of range is the distance between the smallest and largest data value. Okay. So the distance between the smallest and the largest data value. Sometimes we don't report it as a distance. Like sometimes we just say the data values. Like on the test scores data set that I made up last time, the smallest data value was a 0. The largest data value was a 98. So we might say the range is from 0 to 98. Or we might say that the range is the distance there, which in that case would just be 98. Okay. So the formula for this, if we want to find the distance, all we have to do is subtract them. So we do the maximum minus the minimum. Okay. Or the largest data value minus the smallest data value. Okay. And this equals the range. So if we think about another set of test scores, let's say. Okay, so let's say this is our set of test scores. So we have 6 values here. If we want to find the range, we just want to take the largest one and subtract the smallest one. Okay, so in this case, we get 53. So it's the distance between the 40 and the 93. The way we find the distance is by subtracting. Okay. Like I said, sometimes the range may be written like this instead. So you don't have to write it like this because this isn't how the book writes it, right? The book reports it as this value, 53. But if you're ever like coming across this in another context outside of this book, you might see the range written like this, which means it ranges from the values of 40 to 93. Okay. So you just write the smallest one and then the biggest one inside of brackets. But we'll use this version where we're just calculating the numbers. Okay. So there's really not much to do here, right? We're just subtracting the largest. We're just doing the largest minus the smallest. So we can just look at another example. And by the way, I'd like to keep showing you guys how to do this in Excel. Okay. So let's write our data values in here. So we got 40, 55, 75, 80, 82, 93. Again, if you don't have Excel, Google Sheets should have a very similar thing. I don't know if there is a range formula. Let's find out. It might be called something different. Let me see. I don't see it here. Yeah, it doesn't look like there's probably a similar formula called something different. I'm not seeing it. It's not sticking out here. So I won't spend a lot of time on this here. But if you really look for it, I'm sure you'd be able to find something like this. So I'll just show you how to do it by hand instead in Excel. So what we can just do instead is we can just write out a function that says equals, and then you can type in the cell of whatever your last data value is. So this would be A6 because it's in the 8th column in the 6th row. And then minus the first one. Okay, A1. And then there you go. If it's out of order, you can quickly sort. So let's say we switch. Let's say we have the same stuff, but we just typed it in like randomly, right? Okay, so now this wouldn't allow us to put in a, we couldn't do the same thing. We'd have to manually pick out what the smallest and the largest is. Here it's fine. But what if we have like 1,000 data values, right? Then what we could do is we could highlight it. So let me back up here. You want to click on the first one and then hold the mouse click and drag it down to the last one. So it's all highlighted. Then you want to right click, and then we can go ahead and sort. So you can do it whichever way you want, smallest to largest, largest to smallest. So let's do it like that, smallest to largest, and then you can make your formula. You can also do a quick analysis here, which will, you can like kind of make it into a table or a chart or something like that. That can be kind of useful. We might talk about that later. But yeah, if you right click, you get some other options here that I never talked about before. This is how you would go ahead and like delete stuff too. Like you can delete it, or you can paste stuff. So yeah, I think that's all to say about here. You can also do a custom sort if you don't want to do like smallest to largest. So yeah, if you have a lot of data, you'd want to put it in order first, and then you can make your formula like I did here. Okay. And of course, just as a refresher, if you wanted to do the median, the median and the mean, you just go down to median, get your data, and there you go. It's 77.5. And then you can go ahead and get your average, highlight the data, and it's 70.83. Okay. All right. So we'll come back to that once we learn about the next formula too, because the next one's going to be pretty tedious to do by hand. So it'll be much easier to do in Excel. So like I said, oftentimes we want to know, we want to look for what's called the standard deviation. What the standard deviation essentially is on average, how far apart is our data from the center? Okay. Is it like wildly different from the center? Is it is it very far from the center? like here, for example, right, we found that our average, our median is 77.5. So that's the exact center. Well, on average, like how far apart are the rest of the data values from the center? Like 75 and 80, they're not very far at all. 40 is kind of far, and 93 is kind of far. 55 and 82 are medium distance. So on average, how far apart are they? So that's what the standard deviation is. So we're going to build up to it first. Let's talk about just what's the deviation mean, right? Before we talk about the standard deviation, what is a deviation? Specifically, a deviation from the mean. Okay. A deviation by itself just means how far away is something. Okay. If you're talking about something deviating, you mean that it's going away from the norm, right? So here we're talking about how far does something deviate from the mean. So a deviation from the mean is going to be just the distance between that data value and the mean. So it's the data value minus the mean, okay? Which we can write as x minus x bar, okay? Where x is our data value. If you like index them, if you put the data values in order, maybe you'd write it as xi. This is like the notation that we were using here, right? Where x is our data values, and here xi is where you number them, right? But the book just has it as x, so I'll just leave it as x for now. So we do x minus the x bar. Now, one thing that can kind of stick out to us immediately, let's use this data for an example here. Let's tweak it slightly so that because notice we got 70.83 here. So let me change this so that we get a whole number. I'll make this number 76 instead. So now our mean, this was the mean, this was the median. The mean is 71. That'll make it a little easier, so we don't have to do any decimal subtraction. So let's look at our x, which is a data value, and the deviation, which is x minus x bar. Okay, and we'll put it in a table here. So our numbers were 40, 55, 76, 80, 82, 93. Okay. So here's our data values. Here's our deviation on the other side. So we need to do x minus x bar. Remember, x bar is the sample average. So x bar, I'll just write over here, I guess, is 71. Right? That's just what we got from our Excel here. Or to do it by hand, you would add them all up and then divide by 6 because there's 6 of them. This data here. So we want to do, for this one, 40 minus 71. Okay, so we're going to get a negative 31. So we're going to get negatives here. So let's talk about that for a minute. Usually when we talk about distance, we usually report things as positive numbers, right? Like for the range, we set it up largest minus smallest so that we're always going to get a positive number. So what the negative is doing here is it's just basically telling us which side of the mean the number is on. So if it's a negative number, it's below the mean. And if it's a positive number, it's going to be above the mean. So the negative 31 is telling us that 40 is 31 values below the mean. Okay. So the negative, it's just basically telling us the direction. Okay. When we talk about the standard deviation, like about the average, it's basically the average deviation from the mean. We're going to do something so that it's always positive. Okay. But here we're leaving the negatives intact so that it tells us in which direction we're looking. Are we looking below the mean or above the mean? Okay. So 55 minus 71 is going to be negative 16. Okay. 76 minus 71 is 5. 80 minus 71 is 9. 82 minus 71 is 11. 93 minus 71 is 22. Yeah. Okay. So we have 2 things that are below the mean. We have 4 things that are above the mean. So here's our deviations. One thing that you might notice, or might not notice because it's not super obvious. If you add up all of the deviations, you should always get 0. Okay. So if we go ahead and do that, in my calculator here, we'll do negative 31 plus negative 16 plus 5 plus 9 plus 11 plus 22, and we do get 0. Okay. Oops. So, like I said, when we talk about the standard deviation, we don't want to have negatives. If we're talking about on average how far away is our data, we want to look at things below the mean and above the mean equally, right? So we want to make everything positive. There's 2 ways we can essentially make things positive. One, you can just make it positive by doing what's called the absolute value. The absolute value of a number just makes the number positive. That's all it does. Okay. If it's negative, you make it positive. If it's already positive, you leave it positive. The other thing is you can do what's called squaring it. Okay. Squaring, remember, is when you multiply a number by itself. If you multiply a number by itself, it's always going to be positive. Because if it's already positive, then you're multiplying it by a positive and you get a positive. If you take a negative number and you multiply it by itself, then you're doing a negative times a negative, so you're getting a positive. Okay. So the next thing we want to do is square it. So why do we want to do squaring over the absolute value? Well, there's some more technical reasons for it that we really can't get into without going outside the scope of this class. Just know that there is a reason that we go with the squared instead of with the absolute value. And we do make up for the fact that we're squaring it at the end, because you'll notice, like, when we square something, like with these numbers, we're going to make them much bigger, which no doubt is going to throw our calculations off. So at the end, we're going to kind of have to undo the squaring. But the function of the squaring is essentially just to make the number positive. Okay. So the squared deviations from the mean literally it just means that we're going to take the numbers and we're going to square them. Okay. So let's just take what we have here. Whoops. I think I have to use the mouse. Hang on. Let's take our chart, copy it. You copy and paste it right here. In fact, let's shrink it a little bit so we have some more room. And now we'll add a third column called the squared deviation. Squared deviation from the mean still, but I don't really have room to write that. So x minus x bar squared. So we're going to square it. As a reminder, x minus x bar squared is equal to x minus x bar times x minus x bar. So you just multiply whatever it is, you just multiply by itself. Okay. So that's something you should hopefully remember from Math 099 or an equivalent class. But just be careful, because I often see the mistake of taking whatever's in here and just multiplying it by 2. But that's not what we're doing. We're multiplying it by itself. Okay. So a squared deviation here, it would be negative 31 times negative 31. We're taking the number and multiplying it by itself. When we do negative 31 times negative 31, we get 961. And then we do 16 times 16 to get 256. Or rather, negative 16 times negative 16. Either way, we get the same thing, though. 5 times 5 is 25. 9 times 9 is 81. 11 times 11 is 121. 22 times 22 is 484. Okay, so we can just do all of this in a calculator here. Okay. There's another example going on in the book too. I just didn't want to use the same example as them so that you have 2 examples to look at. So if you want to see another example, it starts at right underneath the deviation from the mean on page 47 of chapter 2. Okay, there's a table. All right, so all of this is to work up to the standard deviation. Okay, so before we find the sample standard deviation, we first want to find what's called the variance. Okay. So the sample variance the variance is kind of exactly what it sounds like. It's a measure of how much our data varies, and it's very close to the standard deviation. In fact, it's the square of the standard deviation. So typically what we do is we find the variance first, and then we take the square root of it to get the standard deviation. Okay, so the variance is just the standard deviation squared. Okay, so because of that, we write it as s squared, and we're going to write the standard deviation as s. Okay, now essentially what we want to do here is we want to take the average of all of these numbers. So we want to take the average of the squared deviations. Okay. So to do that, we would add up the squared deviations. Okay. Remember sigma here? This capital sigma means to add them up. So we add up all of the squared deviations, which are these numbers here. And then we would divide by however many there are. Now, this is where the difference between sample and population come into play here. For more technical reasons, what we find out is that if we divide by n, being however many there are, it doesn't give us a good estimate for the population variance. And remember, that's typically what we're doing when we're looking at the sample variance. We're using it to make estimations about the population. If we dig into the more technical details, what we find is that by dividing by 1 less than the total amount that there are, we get a much better estimation. We get what's called an unbiased estimator. So if we do it this way, it ends up being biased. Bias just means that it's always going to be a little bit different, right? Bias is something we typically want to avoid. So by dividing by 1 less, aka n minus 1, we make it unbiased, and so we avoid that bias. So you don't need to understand the technical reasons. You just need to remember that we're not dividing by however many there are in this case. We're dividing by one less. So this is our formula for the sample variance. So for our example here, for above example, we're going to have 961 plus 256 plus 25 plus 81 plus 121 plus 484. So we're adding up the last column here. Okay, this says add up the squared deviations. That's what the symbols are telling us. And then our n here is 6, right? That's how many we have. So we want to divide by one less than that. So we divide by 5. Okay. And so what do we get? 961 plus 256 plus 25 plus 81 plus 121 plus 484 is 1928. Divide that by 5 and we get 385.6. Okay. 385.6. This is the sample variance for this example. Let's look at it in Excel and see if we get the same thing. Okay. The variance. So we just should be looking for a formula that says variance. That's the easiest way to do it. And when you get here, you'll notice there's var.p and var.s. And if you look at the descriptions, var.s is estimating variance based on a sample. Var.p is estimating variance based on a population. We're looking for the sample variance specifically, so we're using var.s. Then you just highlight the data, and there you go, 385.6, which is exactly what we had here. Okay. Highly recommend just doing this in Excel. Okay. This is an online class. So when you're taking the test and doing the homework, you're typically on your computer or phone anyway. So I would recommend using Excel or Google Sheets or something like that. Like you may even just be able to type this into Google. Let's test it. If I type in sample variance and then I type in like 12, 15, 17 or something like that. Well, it doesn't give you the answer. Google doesn't do the answer, but it does pull up a variance and standard deviation calculator. So like I just clicked on the first one, statistics how to, and then you can type in your data and you can get the standard deviation and variance for that. So there's online calculators for it. If you don't have access to Excel, like on your phone or something like that, there are mobile versions of that in Google Sheets. But there's just online calculators if you prefer that way too. So I would recommend doing it this way because then you skip the step of having to find the deviation, having to find the squared deviations, adding them up, dividing by the numbers, having to remember what all these symbols mean. But you should know how to read this. So you should remember what these symbols mean so that when you're reading about it, you know what they're doing. You should be able to look at this part of the formula and recognize, oh, they're finding the sample variance here. Like if you were reading a statistics paper or something like that, right? Now, again, like I said, we were building up to the sample standard deviation. The sample standard deviation we represent with the letter S. This one is S squared because this is just the square of the standard deviation. So to go from S squared to S, we take what's called the square root. Okay. So we take the square root of all of this stuff. The square root is a function which if you take the square root of something, you're asking what number times itself gives you this number. So this is not typically something you can do by hand. It's something you're going to need a calculator for. So for this example right here, S is going to be the square root of 385.6. Okay. So if you put this in your calculator, you're going to, so this is one way that Android and iPhone calculators will differ. On an Android calculator, you're going to press the square root button, then press 385.6, and then press equal, and it gives you, it's going to be a long decimal, so more appropriately, we should say approximately equals, because we're rounding, to 19.64. And you can round to however many decimal places you want. On an iPhone calculator, you're going to type 385.6 and then press the square root button. So Android, you press the square root button first. iPhone, you press the square root button last. Okay. Unless the iPhone calculator has drastically changed. I haven't looked at it in a couple of years, but that's what it was. You can test it here. Try taking the square root of 385.6. Make sure you get 19.64. Back to Excel. Standard deviation, which we'll usually abbreviate SD. We're going to go to the formulas. Go look for standard deviation. You see it abbreviates to STDEV. We want the sample standard deviation, so we're going to do .s. And we're going to highlight our data, and it'll return this number. So it didn't round it to the same place I did, but it's the same number. I think Excel always will round. Well, I think it just depends on how much space you give it. See? So if I expand it out, it gives you more. If I shrink it, it'll give you less. Okay. So again, highly encourage you to just do this in a calculator. I mean, in a calculator or in Excel, right? You just find the function. Just to show you again, you find it, highlight the data that you want. It gives you the number right here, but if you click OK, it'll put it in there. Okay. So, now another question is, okay, how is the population standard deviation different? If we just look at the actual numbers here, what would be the difference? The standard deviation, the population standard deviation, did it here, is 17.9. So why is this so different? Well, like I said, we needed to divide by one less than the number there are for the sample standard deviation. That is how we make sure it's a good estimate for the population. If we're just calculating the population, calculating from the population, we don't need to do that. We don't have to worry about it being a good estimator, so we can just divide by the actual amount. Okay. So the population, first we'll look at the population variance. Okay. The notation is going to change here. Remember, for population, we're typically using Greek letters. Here, we're using the Greek letter sigma. Sigma might sound familiar because this is sigma. This is a capital sigma. Here, we're using lowercase sigma. So lowercase sigma squared is what we use for the population variance. The formula for this is the exact same, except on the bottom, we're going to have big N and we're not minusing 1. So it's just the number in the population. The top is the same concept, but we're using the population mean. So we're using mu instead of x bar. But it's the same idea. It's the mean, right? And then sigma is the population standard deviation. whoops, sorry. Sigma squared doesn't have the square root, right? And I also forgot the sigma, the big sigma. Sorry, correct that formula there. It should be just basically the same thing as this with our different notation, right? We have just big N on the bottom, and then we have mu instead of x bar. Now with the standard deviation, that's where we take the square root. So for the population standard deviation, we just write sigma, lowercase sigma, and then we take the square root of all of this. Again, normally when we're calculating this, we're calculating it from a sample. So this is the more important one to focus on. But you should still know the difference with the denominator here. So let me talk a little bit about what we're using standard deviation for now. Okay. As the book says, and as I kind of said earlier, the standard deviation is a measure of the average distance between the data values and the mean. So we're just finding the average distance. Remember, the x minus x bar, that's the distance. Now, because we squared them to make them positive, at the end, we want to take the square root to undo that squaring. Okay. So we first find the distance, then we square them, then we find the average by adding them all up and dividing by however many there are. And then at the end, we take the square root to kind of make up for the fact that we squared them. Okay. So it's just like taking an average. It's kind of just, we have to tweak a few steps to make the formula what we really want it to be. But it's still representing the same thing. It's representing, on average, how far your data values are from the center. Okay. Okay. I think this has probably gone on very long. 42 minutes. Second half of this chapter, or this section, is pretty unrelated. So I think we won't talk about that part of it yet. Let me see if there's a good example to go through. Here, I'll just make up another example, I guess. Or we can use... Yeah. Okay. Here's something I forgot to do. What does the standard deviation say about our data set? Okay. So our standard deviation was 19.64. Here's our data set. Okay. The standard deviation, it was 19 point whatever. So we're saying on average, our data is about 19 points away from the center. Okay. So it's pretty far spread out, right? That's almost 20%. Which on a test it's huge, right? Like that's the difference between 80 and 100 or 80 and 60. So the data is pretty spread out. You know, this is a very small data set, so it's maybe not as useful right here. But imagine like if we had like 1,000 data points, right? It's impossible for us to really get a grasp on what's going on by looking at them individually. So the standard deviation, it would tell us like, okay, your data is pretty spread out on average, or it's not that spread out on average, meaning it's very like centered around the mean, or you have a lot of things that are very far away from the mean. Okay. You'll often also hear the expression like, these things are one standard deviation away from the mean. One standard deviation is going to be this distance, right? 19.64. So if we're talking about being within one standard deviation of the mean on this one, what was our mean? 71. So one standard deviation from the mean is in the range 71 minus 19.85, 664, right? Minus 19.64 to 71 plus 19.64. So this is what they mean when they say it's one standard deviation away. Whoops. Which can put in the calculator here. 71 minus 19.64 is 51.36. 71 plus 19.64 is 90.64. Okay. So this is one standard deviation from the mean. And you can see the majority of our data actually falls in this range, everything except for the first and the last one. This is often something they'll talk about, or they'll talk about like 2 standard deviations from the mean, stuff like that. It probably won't ask you to calculate that directly. It's more common for us to talk about quartiles and percentiles, which is in the second half of this chapter, rather than how many standard deviations away something is. Okay. So I think this is all I want to talk about on this section. So we worked up. So remember at the very beginning we talked about range. Then we kind of worked up to what standard deviation is. Showed you how to do it with the formula and in Excel. And then we talked about the meaning of it. Okay. So it's a measure of it's the average distance our data is from the mean. And then what does it mean when you'll often read about like something being one standard deviation from the mean, etc. Okay. All right. So that's all for today. The second half of 2.3 we'll do next time, and also probably go into 2.4 at the same time. There's not a lot to do in 2.3. It's just kind of different. So we'll talk about that next time. And in 2.4, that idea of one standard deviation from the mean and 2 standard deviations from the mean and stuff will become more useful. So I'll review it when we get there. Okay. So, as always, if you have any questions, please email me or send me a message on Canvas. And thank you for watching this video today. And I will see you for the next one.